Okay, we're going to now set up a model for optimum crashing or the minimum cost crashing schedule. So we are given for each activity normal time, normal cost, crash cost, and we have already computed all of this. So we need predecessors and successor to be able to set up our earliest start time, earliest finish time, latest start time, latest finish time, like what we did previously. Okay, so I'm going to copy paste the predecessors and successors that we did earlier. Okay, so let's copy paste that here. Okay, so we have that. So now what we're going to do is we're going to set up a model where we are going to determine how much crashing we are going to do for each activity, right? So we're going to do that in this table, and initially, okay, so this is what is going to be weeks crashed. This is what we are after. We need to determine how much to crash. Okay, we don't know that. We're going to use solver. Okay, we did a lot of solver problems previously. So we're going to use solver to get these values, but we have to first set up a model. And we don't know the values, so we're going to leave this blank for the moment. So solver will figure out what those numbers must be. So once solver figures that out, then the actual duration, the actual time, okay, so we can even call this actual time. So we have normal time, crash time, and actual time. Okay, so the actual time will be, okay, so normal time minus how many weeks are we going to crash. Of course, right now it's all blank, so C21 will be 0, so actual time is normal time. But once we set the model up and run solver, then whatever solver puts in here, suppose solver puts in 1 here, then the actual time will be automatically adjusted from normal time down by 1 to the actual time. Okay, so let's copy that down here. All right. So what we now need to do is to set up the model based on the actual time. Okay, so when we run the model, when solver figures out how many weeks are crashed, the actual time will be adjusted for what we are crashing, and all these values will be automatically updated. Okay, so ES, okay, so we have project start time, so that's our starting block. Okay, so that is 0. Okay, so project duration, that is our ending block. Okay, project completion, right? So initially we have, okay, let's earliest start time for A, okay, no predecessors, so it is the start time. Now earliest start time plus, okay, remember it's not it's not normal time, it's not crash time, it's not weeks crashed, but it is start time plus the actual time. So the actual time is adjusted for normal time, adjusted for crash time. So that will be our finish time. Okay. So now earliest start time for B is 0. For C it is the finish time of A. For D it is the finish time of B. For E it is the finish time of C. For F as well. For G and H, so here is the problem. For G and H, when we use max, okay, which is what we did previously, right? So D and E, so we have D and E, okay. So this will work if you're not using solver, okay. F and G here, okay. Okay. So we have to do something about the solver. If it is a linear, remember the solver method, simplex LP, it cannot, if you have max, then you're introducing non-linearity. So that's going to be a problem. We have to fix that. But for now, let's leave it as max, and let's see what happens. Okay, so project duration, again the same thing. So you're going to use max, right? Um, okay, so if you have if there is only one, if there is only one ending activity, then it's not a problem. But so if you're using max, then it is a problem with respect to the simplex method. So we'll have to fix that as well. So the backward pass will be that, and this will be that minus the actual time. So now we can copy that all the way back. It's messy, so you have to clean up the mess. Okay, don't just leave it like that. I will deduct points if you leave things messy. All right. So for G it is H. Okay, so here are the successors. F also H. And E successor is G. D successor is G. C successor is min. Successor, it doesn't matter because we are not going to be using this part in LP solver model, so it's not a problem. So EF, right? Okay, and B it is D. For A it is C. Okay, now slack is latest finish time minus earliest finish time. Copy that. Okay. Now if you want to minimize the project completion time by crashing as much as possible at the cheapest possible cost, okay, so we can then go to data solver. All right. So set objective cell will be project duration. Say we want to minimize that. What is the smallest possible project completion time? By crashing, okay, figure out how much to crash. Okay, and what are the constraints? Well, you cannot crash more than what is allowed for each activity. So we've calculated that maximum crashing allowed. Okay. Now here, okay, that's good. You don't want negative crashing. So make unconstrained variables non-negative. But you cannot use simplex method because of the max. So if you don't change this, it'll give you an error. See? So it's a non-linearity problem. So we have to go and change this to GRG nonlinear, then it will work. Okay, so it will give you, so a small problem like that, like this, is really not a big deal. So you can use nonlinear and it'll still be okay. But in larger problems, not being able to use simplex method can be an issue. So we have to change this max, somehow remove the max and introduce linearity to it. And you can also have other constraints, like instead of crashing as much as possible, you may say, okay, I want to be able to crash such that we have a due date. Suppose we want to achieve a due date of 12, okay, not all the way down to the least possible project completion time, okay, and at the least possible cost, right? So in that case, our model has to be slightly different. So we have the normal cost is that, right? And crashing cost is some product of how much crashing we are going to do. Okay, a crash cost per week. So this will give us how much will be the cost of crashing, and when you add the two, you get the total cost. And we want to minimize that with this as the constraint. So you're no longer, you don't want the objective function to be project duration now, you want that to be the cost. Okay, and you add a constraint that the project duration has to be less than or equal to the due date. Okay, so you want to minimize the cost, crash only as much as needed to get to the due date at minimum cost. Okay, again non-linear because of the max function. Alright, so now we have an answer. Now if you want the crashing to be whole number, right? Okay, then we can add the constraint, add that to be integer. Okay, so when you do integer, then you have to make sure that the options are set properly. So ignore integer constraint, that should not be checked, because if this is checked, then the integer constraint will be ignored. The default integer percentage optimality is 1, which is if you get to close to 99% of the objective function, the branch and bound algorithm used for integerizing the values will stop. So if you want the absolute minimum, then you have to change that to 0%. And of course, when you do that, then the program may run for too long. All right. Okay, so this again uses non-linear solving method. Okay, you have to make some changes to this model for us to be able to use simplex method, which we will look at in the next video.